All right, let's talk about black holes and curved space-time. So we're going to introduce the concepts of general relativity, which is what Einstein came up with. His theory of relativity explains or comes up with this concept of space-time and gravity as being linked together. We can talk about the successful experiments that have been conducted involving relativity, the behavior of time in relativity, what it means, and then how that relates to or explains what a black hole is, what the evidence for a black hole is, and a new era of astronomy called gravitational wave astronomy. Okay, so the first thing that's really important to understand is general relativity in general. Okay, so main goal is here just to discuss the main concepts of relativity, and that gravity and acceleration are the same phenomena in terms of our experience. This was a big deal, and then at the end of the day, this is why we need general relativity to explain black holes. Okay, so Einstein basically came up with his famous theory, the theory of relativity, special relativity, in 1905. And it wasn't until 1915 that he extended his theory of relativity to general relativity. So what Einstein says is that the speed of light is constant for all observers. So if you're on a train and you shine a flashlight, you'll see the light beam, since it's a fixed speed, go up and come down. Okay, that's a certain distance. Now, if I'm watching this happen from the ground, the light doesn't go straight up and down. The light appears to trace out a triangle because the car is moving by as he watches. So hopefully everybody can agree that that length d is different than this length that we can call L. So since the speed of light is constant for every observer, they both agree on the speed of light, c we call it, but they disagree on the length that the light traveled, the path that light traveled. So this is the crux of relativity. It's all relative. So if you're moving, you see lengths, or if you're at rest and you're watching someone move, you see lengths contracted. You see time dilated. Time doesn't appear to take the same amount of time. So the two observers, one on the train and one on the ground, they agree on the speed of light, but they disagree how long events take, when they took place, and the different lengths of different things while they're moving. So this is the crux of relativity. General relativity says that space, which normally, if you remember any math, you just have y equals mx plus b to explain the geometry of a line, for example. If you want to know how long a line is, and this is x and that's y, then this is the square root of x squared plus y squared. Those are all equations that work when your space is what's called Euclidean. And Euclidean geometry is simply flat geometry, equal spaces, whatever. Well, what happens if your space is no longer flat but is curved? So if you want to go from this point to that point, that distance no longer is this squared plus that squared square root, because these distances are curved. So the mathematics to calculate the distance between 2 points in Euclidean geometry is simple. Square root of x squared plus y squared, figure it out. In curved space, it's much more difficult. You need tensor calculus is the mathematics you use to do that. Okay, it's not difficult now if you studied it, because we've figured it out. If you had a good teacher, you could learn it, so it's not. What was challenging for Einstein was he was the first one that sort of applied this to reality, and he said space and time are curved by gravity. Gravity is the result of space and time being curved. So he had to figure out all the mathematics with some other mathematicians and link all that stuff together. Okay, so that's the crux of relativity, is that the speed of light is constant for all observers. Since that's the case, since people are moving around, that obviously leads to conflict between the distances light travels in a given reference frame. So that means people disagree on how long things are, how much time elapses, and those effects lead to gravity in a curved space. So the main principle of general relativity is the principle of equivalence, which says the force you feel standing on the Earth is the same as the force you would feel if an elevator goes up. As soon as the elevator starts going up, you feel a force down. Okay, that is the principle of equivalence that says acceleration and gravity are the same. They feel the same. They don't have any measurable differences. So for Einstein's purposes, he assumes then that gravity is just an acceleration like any other, and gravity is causing the acceleration, but it's actually the flow of space-time around. So the idea that free fall is indistinguishable and equivalent to zero gravity is called the equivalence principle. Okay, so if you can't tell, the area around you is moving, then you may as well be at rest. So free fall, no, zero gravity is the same thing. So then that's this whole thing. What does this mean? Is it gravity pulling you down, or is something accelerating you around? You wouldn't know. It'd be hard to tell. And what this is trying to show you, if these two people jumped at the same time, they would fall at the same rate. From their perspectives, they would toss the ball back and forth. They wouldn't be able to tell that they're falling, because from their perspective, they'd be able to play catch just the same, because they're moving down at the same speed the ball is. So this is a confusing diagram. But from their perspective, the ball goes back and forth. From our perspective, it makes this curved path because it's falling too. So this is just, again, this equivalence principle. So what are these guys doing in free fall on the International Space Station? Yeah, they're in free fall. And the reason they're in free fall the reason they experience zero gravity is because they're actually in free fall around the Earth. So they're constantly, the Earth is here, this, the space shuttle or the International Space Station, whatever it is, as they go around the Earth, what's happening is they're constantly being pulled towards the center of the Earth, but they're moving horizontally fast enough to constantly outrun the path of the Earth. Okay, so one of the key things about gravity that Einstein realized is that gravity affects light too, just the same. Light falls at the same rate that apples do, or anything that you push off the table, or your cat pushes off the table. So the idea here is, this is, again, it's a confusing image, but the beam of light, so it says, in a spaceship moving to the left in its orbit around a planet, the light beam from the rear, bing, starts at A, moves forward B to the target. The ship is falling out of the path, so erase this. There we go. So we might therefore expect the light to strike at B prime above the target. Instead, the light follows a curved path and strikes C. So the idea here is that the ship is falling. We shot the light ray, and maybe you'd expect it naively to continue going forth, but it follows the same curved trajectory as the space shuttle. So the idea with space and time is that gravity, according to Einstein, bends space and time. It turns a Euclidean space, a nice flat geometry, into a curved geometry. And then in order to determine the equations of motions for something moving around in a gravitational field, you need to consider the curvature of space and time. And that's what gravity is. It's a result of the curvature. Okay, so space-time and gravity. The idea here is that gravity, according to Einstein, is the warping of this flat space. It becomes curved in the presence of something like the sun or the earth. And then Newton says for every force there's a acceleration, and then Einstein says the same thing, but it's a little bit differently. The mass of a planet curves space and time, and the curvature tells the mass, another mass, for example, how to move. So it's really crazy. When we link the mass, which causes a warping of space and time, and then we link space and time and mass together, we create this thing called space-time. So space-time is 4 dimensions. It's your x-coordinate, your y-coordinate, your z-coordinate, and the time that you are doing something. All 4 of those things actually are linked together, and we usually draw them as x, y, z, and t as a single object, because if you move around in x, you'll also move around in time. If you move around in x, y, or z, you're also moving around in time too. So your 4 coordinates all change, and if you want to predict where someone's going to be in the future, you need to keep track of x, y, z, and t. Well, it turns out gravity changes t and warps t just like x, y, and z. So it gets a little bit tricky, but the idea is right here, according to John Wheeler, who is an extremely famous dude in the science world. Matter tells space-time how to curve, and space-time tells matter how to move. And that's the idea here, is that you have a nice flat space, you drop a sun in it, your space gets curved, and now planets orbit along that curved space, and that's the big idea with general relativity. Okay, so yeah, space-time, this is a typical space-time diagram. It's usually x and time, or x and y and time. It's hard to draw 4 dimensions on a 2-dimensional thing, so it's not usually x, y, z, and t. That would be more of like a film or a movie that you could see x, y, z, and t at the same time. 3-dimensional movie. But basically, the big idea here, if you're going to take anything away from this, it's that you cannot go from a point 0 kilometers. You cannot move 200 kilometers in an instant. You cannot go there in 0 time. So a space-time diagram shows how 2 events, for example, if you started at A and I started at B and we wanted to meet at this point here, you would have to travel 100 kilometers and I would have to travel 100 kilometers to meet you there. But we couldn't just go instantly be there at the same time. No, we'd have to march forward and over, and that's what's happening here. We're going up in time and over in space. So anytime you're moving around, anytime you're doing anything, you're marching forward in time. So there's a limit of where you can ever be in the universe. Right now you're stuck on Earth, for example, but maybe that's because you don't have a car or money or something. But there's also a physical limitation. Even if you had the fastest thing, even if you could travel at the speed of light, you could not go from here to here instantly. There would still be a finite amount of time for you to travel 200 kilometers, even at the speed of light. So that's the main thing. There's a fundamental limit to causality, that is the speed of light, and this space-time diagram allows you to calculate that and think about that. Okay, so this is another way, this is an analogy for space-time. This is a bad analogy. It's an approximation. It gets the job done in some sense, but it's really difficult to imagine what 4-dimensional space-time looks like when it gets curved. So you just imagine 2 dimensions getting curved into a 3rd dimension, for example. So an ant walking along a rubber sheet, so this would be flat, empty space. An object would continue straight and nothing bad would happen. If you dropped a rock or a paperweight or something onto your rubber sheet, it's going to get this curvature. So if you rolled a ball here, it would kind of get deflected around it. Suddenly, you have this weird mass warping space. If you kind of got it rolling in the right way, it might even orbit this hole. This ant here would probably fall in and not be able to get back out, but the idea is its path is no longer a straight line. Its path is now curved, and that's because the mass here curved the space. So that's what Einstein's theory is it treats all of space-time as a flat surface which can be manipulated by mass. And once you have mass in there and you manipulate it, now that curved space manipulates anything that moves around in it, including the planets, and that's why planets orbit, because there's this dimple created by the sun and everything's orbiting that. Okay? So that's the idea. So what are the tests of general relativity? There's all kinds of stuff, and it's been 100 years at least, 103 years, 105 years since Einstein came up with this theory, and we've been testing it and testing it and testing it, trying to find a hole in it, because we need something to explain black holes, because we'll talk about that Einstein's relativity does not predict what a black hole is, just that it can exist, but it cannot explain what's happening inside of a black hole, because it makes literally no statement or comment about it. The mathematics do not treat that as a thing. So one of the first things that Einstein's theory predicted was what's called the perihelion of Mercury. And basically what happens is, as Mercury goes around the sun, it spirographs around. Okay, and the idea, Newton couldn't explain that, Kepler's laws couldn't explain that. That's just a tiny little perturbation there. A perturbation is a slight change to normal motion or normal behavior, and it's because the space is curved there, according to Einstein, and then that's what causes this slight rotation, because the sun and Mercury, as Mercury goes around the sun, the ripples in the space-time that are causing this Mercury to change slightly, that can only happen with general relativity, space-time. Okay, so general relativity predicted that the curvature around the sun, it's going to have this effect, and that was the first sort of like, whoa, okay, that's pretty cool. The next thing was, there's a great show called Einstein and Eddington. I think it's on Netflix, if I remember. Anyway, Google that. It's a great show. And it's about that Einstein says, okay, if the sun is here, then it's going to warp the space around it. So if there's a star right here, then the light from that star, instead of going through the sun, the light is going to leave from the star and then get bent towards Earth. And then it'll make the star appear like it's coming from over there, because the light ray from our perspective is coming from here. We can't see that it turned around the corner. So that's what, remember what Einstein says, is that gravity is curvature of space-time, which means light falls towards the sun. It gets deflected by the sun in the same path. So if you've got a star here, instead of the light coming towards the sun, all the light leaving the sun, some of it is going to be warped around the sun, making the star, giving you the illusion that the star is up there. And that was a 1919 solar eclipse. They blocked out the sun with the moon, and well, they didn't, but the moon blocked out the sun, and then they took pictures of the stars and compared their locations during the eclipse to where they normally are. Sure enough, they were displaced, and they were displaced exactly according to Einstein. So that was a really big deal. Excuse me. So those were two of the main tests. There's the GPS system that uses relativity to keep track of the time ticks slower near the surface of the Earth than it does out in space where the GPS satellites are. So they constantly have to be resyncing with the clocks on Earth to make sure that they stay in time with each other and with us on the ground, with our watches on the ground. So that's another application of relativity. Okay, so this 1919 eclipse was a big deal, and that made Einstein super famous. Okay, so in special relativity, you can think of it, if your line is this long and suddenly it's curved to be that long, this is longer. Let's say that's your experience of time. Your time is going to be experienced longer. Your time is going to be experienced shorter. So depending on the curvature of space-time, you could experience time more slowly or longer compared to someone else. And that all comes down to the fact that relativity okay, so how should I say this? The faster you move through space, the slower you move through time. The slower you move through time, the faster you move through space. So right now, if you're sitting around, you're moving through time at the speed of light. Okay, so because you're barely moving through space. You can start going faster, and the faster you go, the slower time will tick for you, because you're spending most of your time moving through space. There's another effect here, that the stronger the gravity, the slower the pace of time, and this is like the movie Interstellar. The movie Interstellar says that shows the same thing, where the folks go down to the surface of a planet near the black hole, and 7 years expand more quickly than the people up on the spaceship. Okay, so sorry about that. Okay, so yeah, so this test of time, so there's other things here. Like I already mentioned, the GPS clocks, they've got to constantly correct and update for the sun. There's delays of radio waves when going through closer to the sun than when we're on. So when Earth is here, the time it takes, it's longer than just simply the extra distance we have to travel. It's longer because it has to go through curved space. And remember what that means. It's really difficult to imagine. You have to remember that the sun is here. The sun is not, below anything or in some weird hole. This is just showing you that the light will go near and slow down near the sun and then speed back up. And we can draw that this way to just to show that the distance is longer because the space is bent. Okay, and there's another thing called gravitational redshift, which, just like the Doppler shift that changes the colors of light, gravity can do the same thing. It can smush wavelengths, make them longer or shorter depending on the situation, and can make the give you shift your hydrogen spectra to redder light. And okay, so practical applications. I think they're just talking about GPS here again. There's a bunch of practical applications. Okay, black holes. Okay, so what's going on with a black hole? We want to understand the event horizon. They're not sucking monsters. That's not how they work. They're just regular things. The concept of space-time being so warped that nothing, not even light, can escape, and this singularity at the center of the black hole, why that's such a problem. Okay, so remember, after a high-mass star collapses, it collapses down to either a neutron star, right, or a black hole. So you need to get a ton of mass into a tiny spot in order for the gravity to become so strong that light orbits the black hole. And we call the thing a black hole that light cannot escape because it's so dense that any light ray that comes close to it either orbits it, or if it comes close enough, falls into the black hole. Okay? Blah, blah, blah. Yeah, they started talking about stars, dark stars, a long time ago. Maybe the gravity is so strong that light can't escape if light has a constant speed and that kind of stuff. Dark bodies, there's dark stars terminology, bunch of stuff. But John Wheeler's probably one of the most famous of the physicists that worked on the problem of using general relativity to try to understand cosmology and black holes. So the idea here is that when you're on the Earth, there's low enough gravity that light can just fly away. If you're on a black hole, the gravity is so strong that light gets curved back towards the planet. Okay, this is important because gravity does not pull on things. It curves space and curves your future trajectories. So it pulls you towards the Earth, not by a force, but because you have no other option. Your future path in space-time takes you to the Earth because the curvature of your world line intercepts the surface of the Earth. Okay, so same thing with light. These light rays are not being pulled back towards the black hole. They are just following the shortest path in their curved space back to the Earth. So this guy, Carl Schwarzschild, he was in World War I. While he was trying to figure out Einstein's math, he was calculating, on an artillery shell, on a thing you drop on people to blow them up or whatever. There's a little timer here, and you basically set the timer. You rotate the top to, it's a clicker timer, and so you've got an artillery thing that launches at some angle, and so based on the angle that you launch it and the initial velocity you launch it with, it's going to hit your target over here at a certain time later. You don't want it to land. You don't want it to blow up before it lands, but you don't want it to land and sit there too long for them to deal with it. So you want it to blow up right about when it gets there. So they need all these mathematicians over there, or physicists, to calculate how long the timer should be on, so that the bomb blows up when it hits the ground. And in between those calculations, he figured out this Schwarzschild radius. He said, wait, if you get enough mass into this radius, you should get a black hole. He was the first one. He wrote a letter to Einstein. He's like, what is this thing? And it took a while for people to sort of accept that a black hole was a thing. It wasn't until the 60s that people started to really think of it seriously, and then we started to get some indirect evidence, and of course now we have a picture of one, which may or may not I'll definitely show you. Okay, so the black hole myth, they don't suck. Their gravity is not any different than the gravity of something else. If you get close enough to it, you will be attracted to it and then fall into it or onto it or orbit it or something like that. But there's a lot of black holes where planets are orbiting them. For example, if the sun suddenly turned into a black hole, nothing would change. We would keep orbiting it. It would be darker in the sky, but the gravity wouldn't suddenly increase so much that it would pull us into something. If you take the sun and squeeze it down to the size it needs to be a black hole, it can happily be a black hole, and we can happily continue orbiting it, and nothing would change. The overall gravity would be the same. It would just be the intense gravity next to it. You wouldn't want to get close to it. You also wouldn't want to be close to the center of the sun while it's the star right now anyway. So, okay, so blah, blah, blah. So this, you should read this gravity and time machines thing. It's pretty cool. You could go near a black hole, come back, and you'd basically travel into the future. There's no way to travel backwards in time. If you think about all the atoms in a football, for example, and you throw the football, imagine what it would take to turn every atom, every air molecule, every possible thing that happened and rewind it. So that's not possible. There's no way to go back in time. There's plenty of ways to go forward in time, and that's one of the ways, is to travel really fast or go near a very high mass object, and you will essentially travel into the future. Okay, so at the center of a black hole, the math breaks down, and we have 1 divided by 0, and you get crazy nonsense, or you have 1 divided by infinity, and you get 0. So nothing makes sense or you have another one, infinity divided by infinity, which is undefined. So you get nothing at the center of a black hole. Einstein's math, you put enough mass at the center, and the warping just goes down forever, and it never reaches an end. So that doesn't make any sense. Obviously, that can't be the case. So we're trying to figure out what a black hole is still today. So anyway, that's the thing. You can think of a black hole as a star that's very dark. You can't see because of the light. We can see from its presence. So for the evidence of black holes, we can see that they do emit giant jets. So we'll see huge amounts of energy coming from nothing, seemingly nothing. Sometimes we see these accretion disks that show that something is heating these up into a super bright thing. These are some black holes in a binary star system, so it has this sort of situation where one of the stars is feeding some matter onto the black hole, and the black hole is energizing it to be these giant jets. So these are some candidates. Feeding a black hole, it's the same thing. If you've got an accretion disk, it'll take some of that matter and grow in its mass. So the important thing, so we have the Hubble Space Telescope. I'll show you this in lecture. We've got from the Keck telescopes in Hawaii, we can actually see the stars in the center of our galaxy orbiting something in the middle of it, and there's something there, we just can't see it, so we think that's Sagittarius A star, the black hole at the center of our galaxy. Every galaxy has a supermassive black hole at the center. Okay, gravitational wave astronomy is a brand new field. It's a very exciting field, and basically, if a black hole causes a warping in space-time like this, what happens if you suddenly got rid of the black hole? Well, that warping would have to go whoop, and then it would kind of jiggle whoosh, and snap back into into place and release a bunch of jiggle, like a child jumping on a trampoline. Okay, so the idea here is that if two black holes from binary star systems orbit each other until they merge, at the point of merge, you get a huge, obviously a big explosion and everything, but you actually get a giant ripple in space-time that travels out, and that's called a gravitational wave. The first evidence of gravitational waves were from a pulsar that was spinning rapidly. That was the first sort of evidence, because over time it slowed down, and that could only be possible by radiating away the gravitational wave energies. So it lost energy by radiating away gravitational waves. This is LIGO. This is a gravitational wave facility. There's two big arms to this thing. They're each 2 kilometers long. And they shoot a laser beam down and back and down and back, and they recombine the light at the center. And what happens is, normally when the light waves meet back at the center of this thing, they cancel out and you get zero light. If one of the arms is longer than the other arm, then the light waves interfere with each other, and you see a pattern. And if the interference pattern jiggles, then a gravitational wave passed through the detector. So you have two of these things. One here in Louisiana, and the other one is in Washington State. And so the other one is up here in Washington. So if a gravitational wave travels through, you're going to see the signal in Washington, and then you'll see the signal in Louisiana, and the time difference between them will be determined by the speed of light. So you'll be able to tell if a gravitational wave went through, because they'll both see the same signal, and they'll be separated by 1,000 miles or however far apart they are, times the speed of light. Okay, let's see. Well, not times the speed of light, rate times distance. Okay, so yeah, here's the first. This is Hanford in Washington State and Livingston in Louisiana. These are the two signals, and if you combine them, you see that they both have the same pattern. And there it is. Two black holes orbiting each other in their last phases and then merging, and that's what happened. So we've detected a bunch of them now. That was the first one they announced. That was a big deal. We have detected, according to this, 4 more by the end of 2017, so they seem to be happening pretty regularly. LIGO just got an upgrade, so we'll be able to see more of these things. Virgo is another one in Italy, and China is putting on a bunch of them. And so we'll soon have a bunch of telescopes. And the good news about that is, if this is Earth and we have a LIGO here and in Livingston and in Italy and one in China, okay, and then a wave comes through and it goes ding and then ding, 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 the time difference between each of these allows us to triangulate very precisely where the black hole merger or neutron star mergers or whatever came from. So for example, neutron star mergers were detected by LIGO, and they were able to pinpoint where it came from. They followed up with visible light to see the supernova from 2 neutron stars merging, and they were able to determine definitively by measuring it the contents of platinum and gold in the explosion. So that's more evidence that the heavier elements come during nucleosynthesis from collisions and things like that. Okay, so let's go to summary here. So in summary, okay, general relativity is treating time and space on the same footing and saying when gravity or when a big mass gets into space, it actually causes it to curve. And that curvature determines your trajectory. You will follow a straight line on a curve, and that will be your future path when the space is curved. Rather than moving on a straight line, you will follow a curved path. You won't know it, but you will. Okay, and that's what gravity is. It's this curvature caused by mass. We have lots of tests of general relativity. We've got time goes slower if you're near a massive object. Black holes are when the curvature is so strong that not even light can escape. It orbits it, it falls into it. The curvature is so severe. We have tons of evidence for black holes, and we'll talk about that in class. And there's a new field, gravitational wave astronomy, that allows us to measure when black holes merge. Okay, that's everything. See you tomorrow. Bye.